Our first question asks, if Bob and Sally both have stockpiled toilet paper for the quarantine, Bob's family has 30 rolls on hand, but one roll lasts his family 3 days. Sally has less, 20 rolls on hand, but her family is smaller. One roll lasts 5 days. So our first job is to find out the unit rate. To find the unit rate, simply divide the numerator by the denominator. We get 1/3 of a roll per day for Bob's family, 1/5 of the roll per day for Sally's family. If we want to find out when their supply will run out, we're going to take the amount they started with and divide by the amount they use per day. So in this case, it'd be 30 rolls divided by 1/3 of a roll per day. Bob's supply should last him 90 days. Sally starts with 20 rolls, but she only uses 1/5 of a roll per day. Her supply should last 100 days. If you were to graph this, which I did here, you would find that we can see Bob starts up at 30. His supply dwindles steeper because he uses 1/3 of a roll every day, and his supply is exhausted at 90 days. Sally starts with less, but the rate of consumption is also less, so she's going to outlast Bob and make it to 100 days. The second part of the question asks, after how many days will they have the same number of rolls on hand? Well, looking at the graph, I can use the graphing method to solve this system of equations to find that I have an intersection right here. That would be at 75 days, and we have to calculate how many rolls they would have there. So Bob uses 1/3 of a roll per day. That would be 25 rolls. So we're looking at 5 rolls. 75 days, they both have 5 rolls remaining. Now I also suggested that you use alternate methods to solve this system of equations other than graphing. Our first method would be substitution. Here's the premise. We have two equations, one for Bob, one for Sally. Bob's supply can be modeled with 30, the starting amount, minus 1/3 of a roll times the number of days that have elapsed. Sally's supply can be modeled with 20 minus 1/5 times the number of days that have elapsed, or x. Now, because they both have a y in them, we can substitute. So if we know that y on this side for Bob is the equivalent to 30 minus 1/3 x, I can replace this y with this expression because I know that they are equivalent because of the equal sign. So now I get an equation that has only one variable, the x. I get 30 minus 1/3 x is equal to 20 minus 1/5 x. One equation, one unknown. We can solve that using our inverse operations and combining like terms. So first I move my variable terms all to the right and my constant terms to the left. Need to find the sum of negative 1/5 and positive 1/3. When you add two things that have different signs, you find the difference. 1/3 minus 1/5 gives me a remainder of 2/15. So I get 2/15 x is equal to 10. Multiply both sides by the reciprocal, and I find the same answer we did with the graph, which is that their supply will be the same after 75 days. And then the third method we have is to solve by elimination. Elimination operates under a similar principle. Notice I put the two equations on top of each other. Y equals 30 minus 1/3 x and y equals 20 minus 1/5 x. Now we know, just looking at the top equation, we know that we can subtract something from the left as long as I subtract the same thing from the right. Well, I'm going to subtract a y from the left and 20 minus 1/5 x from the right. How do we know that these two things are equivalent? Because of the equal sign in the middle. Well, when you subtract y from y, you end up with 0. Your y term has disappeared. So now we're left again with one equation, one variable. We're going to combine like terms, use inverse operations, subtract 10, multiply both sides by the reciprocal of the coefficient, so times negative 15 halves, and we end up with, again, x equals 75 days. Okay, the second problem has to do with John, who is charging a certain amount for the use of his toilet facilities. You have two options. Option one, you can spend $20 per week and $2 for every bathroom visit. So question A asks, well, what if you have to go to the bathroom 5 times a week? Well, $20 a week plus 5 times $2, you end up with $30 total for the week. Option 2, a $10 fee for the week plus 5 times $3 per visit, you end up with a total charge of $25 per week. Option 2 is the better deal if you only need to use the bathroom 5 times per week. The second question asks, well, what if you need to go 15 times a week? Okay. 20 plus 15 times 2, now our total is $50 a week. Option 2, $10 plus $3 a visit, sums up to $55 a week. So now option 1 is the better deal now that we have more visits to the bathroom. Question C asks to find out what's the point where they're the same cost, where it doesn't matter which option you pick, the crossing over point, if you will. So we have two equations. Option 1 is $20 plus $2 per visit. Option 2 is $10 plus $3 per visit. I'm going to use substitution. Substitute this expression for the y over here, because I know that those are the same thing. Now I have one equation, one variable. I solve for it, I get x equals 10, or 10 visits is the crossing over point. And so if you're going to visit the bathroom 10 times, doesn't matter which option you pick. If it's going to be less than 10 times, you're better off with option 2, paying a little less up front, but a little more per visit. If you're going to go more than 10 times, your better option would be option 1. You pay more up front, but less per visit. So question D, when it asks what your best option is at 12 times per week, you're going to be with option 1, actually, is the better deal. Option 1 is the better deal for more visits than 10. And then let's take a quick look at the graph so that we can see what that looks like. We'll use the graphing application GeoGebra, and you can see here that the intersection point is at 10 visits, and any number of visits more than that, you're better off with, you're paying less with option 1. Any fewer than 10 visits, you're better off paying with option 2. Don't forget to check the links in the problem for instructional videos, practice problems, and solutions on solving systems of equations using graphing, substitution, and elimination.